Welcome to part 2 of cylindrical shells. So we're leaving off on problem number 3. And so what this problem states is that use the shell method to calculate the volume V of the solid obtained by rotating the region under the graph of f of x equals x to the negative 1/2 over the interval 1 to 4 about the line x equals negative 3. So we're no longer rotating around the x or the y-axis, but we've actually going to rotate around a vertical line at x equals negative 3. So that's important to think about. Okay, so the solution to this is if we want to rotate the region under this function f of x over this interval about this vertical line x equals c, we need to know that c is less than or equal to a. Then we know the volume is found by this method, 2 pi times the integral from a to b of x minus c times f of x dx. So we're going to integrate that. So if we do look at this, we know that our c value is negative 3, which is definitely less than 1. So this integral is going to fit. We're going to be able to use that. So let's go ahead and find the volume using this formula. Okay, so the volume, we're going around the y, or the x equals negative 3, so it's going to be vertically around that line. Okay, so thinking about this mathematically, 2 pi times the integral from 1 to 4 of the radius times the height dx. So the radius, is we're moving this, is going to be x plus 3. You know, x minus negative 3, that's going to change to plus, times, and there's our f of x function, and we should throw a dx here to be consistent. So let's go ahead and integrate this. Now the first thing I'm going to do is I'm going to distribute and simplify. So I'm going to multiply that x to the negative 1/2 to each of these terms, okay, which I do here, and I simplify and I get 2 pi times the integral from 1 to 4 of x to the 1/2 plus 3x to the negative 1/2 dx. So now that I have the simplified form, now all I need to do is to integrate. So we're going to integrate with respect to x. So let's go ahead and do that. And when we do integrate x to the 1/2, we get 2/3 x to the 3/2 plus we're going to have 6x to the 1/2. Okay, and then again we have to evaluate that from 1 to 4. So what we do is we plug in 4 for each x, and we subtract off when we plug 1 in for each x. Okay, when you do that and simplify, you should get 64 pi over 3. Okay, so that's the volume. So again, we set up our integral, and this becomes x plus 3 because it's really x minus negative 3. We distributed the function through, and then we integrated. And the last thing you want to do is evaluate by plugging 1 or 4 first into this function and subtract off when we plug 1 into this function. In example 4, okay, what we have here is we're going to use the shell method to compute the volume of the solid obtained by rotating the area under the curve y equals 9 minus x squared over the interval 0 to 3 about the x-axis. So remember, if we go and we're going to rotate about the x-axis, the radius here is going to be from the function to the y-axis. Okay, so that's really important to remember. Even though we're rotating about the x, the radius, in this case we call it AB. So how do we know what AB is? Well, when we solve here, this is just an x value because we're going a length from the y-axis out to some point on the graph. To find that, we just solve our equation for x. When you do that, you get x equals the square root of 9 minus y. In this case, x is AB. So that's important to know. That's our radius. So what does that figure look like? Well, here's the graph in red, and we're rotating it around the x, so we actually get this cylindrical shell here in green. There's our AB, and all these points are rotated around the x-axis. Okay? So that's what we're going to take the volume of. So let's set up the integral. So we're going to end up using u substitution here. We have the volume is equal to 2 pi, and we're going to go from 0 to 9, okay, and we have y times the square root of 9 minus y dy. So when we do that, we are going to let u be 9 minus y. So when we take the derivative du dy, we get negative 1, which implies du equals negative dy. Okay, so we go ahead and substitute u in where needed be here, and we know that du is actually equal to negative dy. So notice how I put the negative sign out here, and we have du here, and from this step to the third step here, we've distributed the 1/2. That's why you have 9u to the 1/2 minus u to the 3/2. We distributed, just like we did in the previous example. Okay, so I picked my u, I substituted my u back in, I distributed the square root of u to both terms, and I'm left here. And now notice how I've gone from 0 to 9 to 9, 0. Remember, in previous sections we talked about substituting our a and b in. So u of 0 equals 9, right? 9 minus 0 is 9. When you plug in 9 in to the function, you get 0. 9 minus 9 is 0. So we're plugging our two intervals, our lower and our upper, into our u function. In this case it would be u of y, and we get our two new values. So that's why it switched from 0 to 9 to 9, 0. So like all other integrations, once we have this function here, we're just going to simply integrate. So we do that in this step right here. So we've integrated, we have 6u to the 3/2 minus 2/5 u to the 5/2. And the negative 2 pi is still up front. And now we're going from 0 to 9. Well, when you plug in 0, since both these terms have a u, it's just 0. So really all we do is have to plug in 9. And let's see what that looks like. And so this is one of the few examples where I showed you what to plug in. And most of the time I'm assuming you know how to plug in. But look, we have negative 2 pi. There's our 0 substitution into what we've integrated. Minus the 9 when we substitute in. Well, this is all gone. This whole part is out. Okay, and we're going to minus, okay, subtract off the 6 times 9 to the 3/2 minus 9 to the 5/2. Okay, so this whole thing is gone here, and we're just left with 648 over 5 pi once you simplify that out. Okay, so that's the second part of cylindrical shells. If you have any questions, just type them below, or you can go ahead and email me, and we will see you next time.